Hi, everyone. My name is Shreya Shankar. I am a PhD student at UC Berkeley, and my advisor is Aditya Parameswaran. And today I'll be presenting our vision paper towards observability for production machine learning pipelines. Machine learning is very tough to put in production, and this is not new. It's well known that building individual components of pipelines is pretty challenging because such components are pretty heterogeneous. And I say that not because it might be different hardware or software back, but because different people also are building these things, from data scientists to engineers to product managers to labelers, you name it. And there's been a lot of progress in the data management solutions that help people build these components. But, bugs come when gluing these tools together and gluing these components together, which makes debugging super, super challenging. So as a result, we ask the question, how do we make debugging and sustaining deployed machine learning pipelines much easier? So we can take lessons from software engineering. Software engineering has a lot of tools for debugging production systems, one notably around observability systems, or the idea of getting better visibility into understanding software behavior using runtime collected telemetry. And this is not just about monitoring known unknowns, for example, like metrics that you might define to monitor at runtime, but it's also about capturing the logs and traces and events that can be aggregated over, such that if you learn of a bug that happened in the past, you can go and figure that out using the previous logs. So this is about helping people diagnose and find unknown unknowns. So it's great we can kind of have something to go off of when trying to think about how to debug machine learning systems, but machine learning brings some unique challenges to the table. One being, changing anything changes everything due to the complex, intertwined nature of components in this pipeline. And also, if you change something, if you think it's an isolated component in the pipeline, or if you have a very small change, these changes can have unintended consequences on end-to-end performance, especially when these pipelines are so dependent on data quality that might not always be inspected by humans, especially in an automated system. So keeping these things in mind, we've written our paper around bringing observability to machine learning. And we argue in this paper that a lot of the challenges are actually data management challenges and would benefit a lot from database driven solutions, more so than machine learning problems for reasons I'll also outline in this talk. We propose a three-pronged framework on detection and diagnosis and reaction to bugs in machine learning pipeline. And in each of these prongs, we deal with these driving questions. First, how do we detect when the pipeline performance goes down? Then, given a poorly performing pipeline, how do we figure out which components have errors? Then, how do we figure out, what's the best way to react to the error or fix the error? And there's a number of challenges in solving these questions, namely in detection. Sometimes we don't even have ground truth for the metrics we want to observe, which is quite different from software. Then magically, even if we knew how well the pipeline was performing, diagnosing is hard because data sets can be really large, very wide, with large numbers of features. And too hard for one human to inspect everything of. And there's been great work from the database community in quantifying data quality with various metrics and constraints. What metrics of data quality, what values of constraints should pull the trigger to alert a user whether data is shifting or data quality has degraded, and how do we adapt that as the data is drifting and changing over time? Finally, in reaction, there's many ways to think about fixing a bug depending on the resources you have. Say maybe a small slice of the population has lower performance. Do we retrain a model for that slice of the population? Do we add a rule to boost that performance? What's the best way to solve this problem without having a data scientist enumerate all solutions? So maybe that gives you an example of how hard these problems can be, which I'll dive into also later in this talk. If these aren't hard enough, bolt-on observability systems also have a real-time component to them. They have to be lightweight so that we can compute metrics and monitor things at runtime. and also log information without hindering performance of the system. And these observability systems need to be interoperable with the wide variety of tools people use to build their own ML pipelines. In this talk, I will cover some challenges around detection and diagnosis. But first, let me get into a missing labels problem, how we find out how the pipeline is performing when we don't have labels. So what does this scenario even look like? Figuring out pipeline performance when you don't have ground truth, or how you don't know how well your machine learning pipeline is doing. So to illustrate this, say we're making some sort of stream of predictions and we're also receiving some stream of labels. Maybe we've made 5 predictions here, and in this case, we don't have no idea how well our pipeline is performing because we don't have any feedback. But maybe we get some feedback, the green makes correct feedback, and we make some other predictions. And at some point, we have a partial feedback scenario where we could estimate the accuracy of the inner join of the 2 streams, but this is not representative of the performance on the predictions made up to that given point, right? What about the unlabeled data points? And then finally, maybe we get all the labels, and we call this the full feedback case, but rarely are we in this full feedback case. Rarely do we get labels for every single prediction that we make. So a real key challenge here is, how do we get better estimates of the performance when we don't have labels? We can draw inspiration from the statistics literature on estimating unknown performance with known labeled data. So when machine learning model, as a background, when ML models are trained, they're typically trained on data sets that are partitioned into training and validation splits, where the validation split isn't actually something that is used to optimize the model's parameters. So it's used to identify whether the model is overfitting or generalizing, or meeting the data scientist requirements. So we can use this validation set because it's labeled. We can use this to get a sense for how our serving time accuracy might look like. And the way to do this is broadly as follows. First, we bucket this validation set to characterize the distribution of data points. Then we can use these buckets and compute the accuracy or the performance or whatever metric we care about for each bucket. And finally, at serving time, we can maintain a histogram of the distribution of serving points by whenever we make a prediction, we figure out which bucket it corresponds to and increment that counters bucket. And anytime we want to have an accuracy estimate, we compute a weighted sum of the pre-computed accuracies from the validation sets. So to give a more concrete example that we have in the paper, we look at the New York City taxi cab data set, where every record corresponds to a taxi ride, and we're trying to predict whether, or the ML pipeline is trying to predict whether the rider gave the driver a tip of 10% or more. So we have the simple bucketing function on the neighborhoods. We tie each record with each tuple with its neighborhood. And on the validation set, say we have these accuracies of 50% and 80% for our model for the neighborhoods Chelsea and Soho, respectively. Well, when we've deployed our pipeline and say we have 100 predictions of Soho rides that are not labeled and 100 Chelsea predictions that are unlabeled, we can do a weighted sum to get an accuracy estimate of 60%. So that's kind of the strategy at a high level. Now let's talk about what we really want to do, right? We want to make these accuracy estimates as accurate or as representative of the true accuracy as possible. So the bucketing strategy matters a lot. On one hand of the spectrum, you could imagine having a very coarse grain bucketing. While this is great because it doesn't take up that much space, it's not very good because it's not very predictive of the accuracy. Like in the most trivial example, if you only have one bucket, well, you would simply be then estimating your validation set accuracy at serving time. That would never change. And so that's not super useful to us. On the flip side of the coin, if you have a very fine grained bucketing scheme, it might take up too much space, might be hard to maintain at runtime, even though it might be more predictive. but it also has a failure mode of maybe having sparse buckets. So if there are validation set data points that don't fall into a bucket, then that bucket might not have an accuracy estimate that can be leveraged at serving time. So in creating these bucketing strategies, we really need to find a good balance between space, sparsity, and predictiveness. And not only do we need to do this dance between these three desiderata, we also need to make sure that the strategy is adapting to the changing distribution of data over time. If we don't change our bucketing strategy, then our estimates can diverge from the ground truth metrics, which is not very good. So this really smells like an approximate query processing problem, as I mentioned earlier. Like a lot of these problems they have to do with data management. So how do we accurately compute accuracy metrics when we don't have all of the data, or we're not using all of the data, labeled data to compute the metric on? But it's a little bit different than traditional approximate query processing literature in that, well, in literature like BlinkDB, for example, the idea is to take a workload of queries on data to compute the best strata or subgroups for. But in our case, we don't really have a workload of queries. We have one query, which is accuracy or the user-defined ML pipeline metric. And our goal is to maximize accuracy on that one query. And we don't know all the labels that we have. We don't get to choose which data points we want to label. So we really want to hyper optimize for this one query, especially as the data is drifting over time. The next thing I'll talk about in this talk, the next problem is around detecting data drift. It's very useful in not just detect monitoring for data drift. It's not only useful in getting good accuracy estimates when you have missing labels, but also it can help with diagnosing which components are drifting or which components need some sort of retraining. So the problem statement is as follows. How do we know when some live data, D prime, serving data, has drifted enough from the training set to result in an accuracy drop? And prior work tells us that we can track divergence metrics, KL divergence or two-sample statistical tests, but it's also well known that these metrics are inaccurate scale and take up a lot of memory. So turning to the ML literature, there's recent work in training models to detect drift. And the idea is to train a model to be able to discriminate, like a binary classifier, to discriminate between the training set and serving stream. And if that model cannot discriminate between the two, so it converges to basically a random classifier, then these two data sets are basically from the same distribution. And this was prototyped at Uber, shown to work offline, and has also picked up traction in the Cadwell communities as a technique known as adversarial validation. But bringing this to a real-time monitoring can be challenging because we shouldn't be training a new model every time we make a new prediction or batch of predictions. That's very slow. So how do we have some sort of incremental training procedure? That's kind of where the data management side comes in. Our insight in the paper is that users don't care about the exact AUC or metric that determines whether this proxy model is a good classifier or random classifier. Instead, we can incrementally fit a model to predict whether a data point comes from the training or serving distribution and look at the loss of this incrementally fit model to determine whether our model is now becoming a better discriminator or not. And we try to do this on the taxicab data, and we find very nicely that the log loss of this incrementally tuned classifier kind of mirrors the metric from the Uber paper that was proposed. So this is great, and while it looks good at a glance, it actually really breaks down for many real-world tasks and metrics. Not all metrics are accuracy, not all data sets are very nice and like equally sampled. So there's a lot of connections to the sampling literature around how do we make sure that we are incrementally fine-tuning a classifier on a representative sample of the stream. So putting this all together and all of the other challenges that I didn't get to discuss in this talk, we also propose a system architecture in the paper around flexible Python instrumentation. executing with low overhead, and then finally having minimal information in the storage layer to cover all sorts of debugging queries. In summary, we talked about how deployed ML models offer new data management challenges for us to solve. And I just got to cover tracking performance without labels and detecting drift in real time. But there are so many more considerations to leverage or to think about when leveraging new ML advances, such as multimodal data, text, images, large language models. And if you're interested, please reach out to me via email at shreyashankar@berkeley.edu. Thank you.